All right, let's have a little discussion about something called the simple machine and what that actually means. We've seen already that we can apply forces to things and cause them to accelerate or cause them to move at constant speeds if we have opposing forces that are balancing us. And we've seen all the different ways in which that can happen. And of course, that means that for humans, when we do all kinds of things, we have to apply a lot of forces. The problem is that humans are not very strong. We're very limited in how much force we can apply. So we have two options. Either we build a machine like, a backhoe or something, or a big tractor that just can simply exert more force, right? One option is to try to figure out how to exert more force. And that requires massive machinery. Well, a good example would be a tractor on a farm or something like that, which can push and pull things with much greater forces than any human could. In the very old days, they would use multiple humans. So if you needed to move something very heavy, you would have gotten 15, 20, even 100 or more people, and you would have attached ropes and push and pull. But of course, that's not very practical. So we invent things like the tractor, which can pull things for us. But there's another way to make things happen. A tractor is a machine, but it's not a simple machine because it's works a little bit differently. Its focus is to increase the amount of force, make the force bigger. What simple machines do is they make use of a very interesting trade-off. I'm going to put the word trade-off here. What they do is they actually reduce the amount of force needed to do something. Instead of getting a tractor that can push harder, a simple machine reduces the amount of force that is needed to make something happen. But it's a trade-off. You can't just reduce the force. You can't just make something simpler. The trade-off is that it increases the displacement or the distance. We could call it distance. It increases the distance over which the force is applied. So what that means in simpler terms, the force is applied. What that means in simple terms is that we can push with less force, but we must push for a longer distance to make up for it. Now let me show you a couple of examples of simple machines. Well, in fact, let's make a little list of the most common simple machines. They are the lever, the inclined plane, sometimes just called the wedge. We could have the string and the pulley. And the other most common one is the wheel and axle. And you'll notice that these are things we find all over the place. We find these little things everywhere where humans do work because they do allow us to reduce the amount of force, but trade it off by increasing distance. But see, that's not a problem for humans because going a little farther isn't a big deal. We're pretty good at going long ways. We're very good at endurance, but we're just not so good at having massive strength. So let's take a look at the lever, for instance. So a typical lever is a long, get a smaller line here. It's a long sort of object like this, and maybe a piece of wood or a board or a piece of metal, a metal bar. And what we do is we put a little rock under it or a little pivot point. Let's make that a little bit lower. There's a little rock or a cement block, anything that the lever can rock on back and forth. And then we stick this end here underneath something large. Let's say we wanted to lift up some big box or something that was sitting here. We wanted to lift it up. And so what happens is then we, of course, pull down on this side. We pull down. This is called the effort force. The effort force. FE for short. Effort force. And then, of course, what that does is it causes a force to push upwards over here on the box, kind of this way. We call this the load force, FL, the load. Now, what's interesting is that these forces are not the same, because the other thing that matters is how far you actually push or pull. If you look at this picture and you were to pull on this lever, if you pull this part of the lever all the way down to, say, here, well, this part of the lever is only going to go up about that far, right? If the lever was level, if you pulled it to level, let's say. So you see how much further this is on this side. You're pushing a longer distance or pulling a longer distance. This is only moving up here on this side a very short distance. And so what we have here is we have a small effort force, but a larger distance. And on this side, what we get then is the same proportion, but reversed. We get a load force that's big and a smaller distance. Right? So it's kind of like if you thought about numbers, if you look at the number, 2, which is a small number, and multiplied it by 10, you'd get 200, right? But you can achieve 200 by using the 10 multiplied by a little 2. So you move less, see the D's are different, but that means that the force sort of reverses as well. Both of these work out to 200. And of course, there is a measurement or a property in physics that we call work. And we're going to learn about that shortly. Work, which is equal to the force multiplied by the distance. And we'll see that what we're really talking about here is how much work is done. In other words, we do the same amount of work, but we do it with smaller force and greater distance instead of larger force and lower distance. So that's the trade-off when you use a lever. And we'll learn how to calculate all that as we look at each simple machine in detail. If you look at an inclined plane, it's kind of the same thing. Let's say you wanted to push this big heavy box, right? Well, if you had a big heavy box and up here is the back of a truck, right? And you had to load it into the truck. Maybe that's the back end of a large truck. Well, if you have to lift the box up to the floor of the truck, then in order to lift the box, you would have to push it or exert a force. Remember, when we're lifting something, the force of gravity pulls down. And so we would have to at least match the force of gravity with our applied force, right? Or to lift it up and put it in the box. Now, if instead we have the truck, here's the back of the truck, if instead we put a ramp here, then what we can do is we can take our box and put it on the ramp. And we can slide the box this way. So instead of lifting straight up, we're pushing or pulling along the ramp on a little bit of an angle like that. That becomes our effort force, the force of effort. But here, what we have to do is we have to compare. You'll notice that when you lift straight up, I'll do it here in red. When you lift straight up, you lift from here to here. That's sort of considered your load force. What you're actually doing is you're getting a box that much higher than it was. But if you look at how far you have to push when you go up the ramp, this distance is actually much greater than this distance. So again, if the distance is greater, the force can be smaller. So the ramp allows us to push the box up into the truck with less force, but greater distance, instead of trying to lift it straight up, which requires more force and less distance. And we will study how that works and the mathematics of that as well. Another example was the string in the pulley. So a pulley is basically just a little wheel that a rope can be wrapped around. And a single pulley has an interesting effect. Because what you do is you grab the rope on this side and you pull downwards on the rope. And if you tie the rope to something over here, well, then when you pull down on the rope, the pulley sort of bends your force and creates a force this way. We call it tension. When you pull on a rope, you make tension in the rope. And the tension now redirects the force for you. So we can lift this blob here, this heavy object, we can sort of lift it upwards or redirect how we want to pull. So we sometimes use a single pulley to redirect the force. But here's how a pulley basically works. To create a simple machine, you use a couple of pulleys together. So you put two pulleys, for instance, on a block. So usually these are connected by sort of a piece of wood or a block of iron or something. They're just kind of sitting like this. And maybe a third pulley goes down here like this. And you have this pulley sort of attached to some big heavy object that you want to lift. Okay. And so in this particular instance, you could actually, you know what? I think I've just decided I'm gonna change that. I'm going to just do a two-pulley system to make it simpler, because maybe adding three is too much right now. So let's just do two, nice and simple. Let's put a pulley at the top and a pulley at the bottom. And let's attach this pulley to our block again, just like this. And let's have this wheel attached up above. Let's say it's attached to the roof or a big joist in your ceiling or a big piece of wood or whatever. So this pulley can't move. It's sort of locked onto the ceiling, whereas the other pulley is just attached to the object. So watch what happens now. We take a rope and we run the rope up over the pulley like this, and it goes around the pulley. And then we bring it down and we wrap it around this pulley. And then we bring it up here and we tie it tightly here so that it doesn't move. And then when we pull right here, we pull on the force, we create our effort force, which is called tension. Whenever you create force in a rope or a cable or a chain or, well, anything really, when you pull on something, you can create tension inside of it. So tension is created in the rope. And what's interesting is that tension is the same all through the entire rope. So what you effectively get is tension. Now, look at the direction. The first pulley up here at the top, right here, that pulley is going to change the direction of my tension. And it's going to wrap down here around this pulley at the bottom over here. So effectively what happens here is I get pulling upwards and pulling upwards. And you can see what's happened. I've created two lifting ropes where I used to have only one. And since the tension is the same in all the ropes, I now have twice as much effort force lifting my block. And that creates more force to lift the block. But here's the catch. If you want to lift this block up this far, in order to do it, you would have to pull this rope right here. You would have to pull it twice as far. It would take twice as much rope than that distance. So you'd have to pull for twice as far in order to get this to move this distance. So again, we are increasing the amount of distance that we move something or that we use, but that allows us to reduce the amount of force. And the last one, of course, is the wheel and axle. So in a wheel and axle, you have a wheel, right? And it's attached to an axle so that it can spin. And you can either attach the wheel to another wheel and have it on the same axle. You can have a wheel that is wrapped by a string or by a cable or a chain. Like on your bicycle, you have two wheels, and the chain goes around the wheels like this and connects them in that sense. And to do that, you often have to have a wheel that has what we call little spikes on it, right, to grab the chain. And the little spikes, the wheel with little spikes is called a gear. So a gear has little sort of spikes or places where it can catch. And the idea is that another wheel could go right beside it, like this, with its little spikes. And as this wheel turns, the little spikes inside here push on each other, and they would cause the other wheel to turn sort of this way. It would make the wheel turn the other way, and the two would turn. But what you'll notice is that the amount of turning of the big wheel, right, when it goes around once around, this little wheel might go around 2 or 3 times because it's smaller. So that means that whatever's attached to this wheel will have less effort force, but guess what? It will go around 3 times instead of 1 time. More distance. More distance. That's what happens on your bicycle. And we'll talk about that also with more detail. And so what we call this, we have a name for it. We call it mechanical advantage. The idea of a machine that can reduce force by increasing distance. It gives us what we call a mechanical advantage. That's what means basically reducing force in exchange for distance. Now, there's 2 kinds of mechanical advantage. There's what we call the ideal mechanical advantage, IMA, ideal mechanical advantage, or IMA for short. And then there's something called the actual mechanical advantage. And we'll learn with each of these machines what that means, but I can tell you generally what it means. What it means, if we go back to all these machines, if you were to sort of mathematically do the calculations, you would find out what the ideal mechanical advantage is. That's sort of the mathematical prediction of what should be possible. But unfortunately, there's this thing called friction, which reduces the effectiveness of all these machines. If I go right back to the lever, and not just friction, there are other things that reduce what we could do. So imagine this board that I showed up here. Well, if you took a piece of wood and you tried to move it, right? Let me just redraw that. If you tried to take your lever and swing it down this way, what you might find is the board might bend a little bit before it starts to move. And that bending is taking away some of your distance, right? If that's where it was before. But it's not doing any lifting down here on the load, so it's kind of like wasted motion. And that means that you're not going to get quite as much movement of your load at the other end. There's also a little bit of friction if you look at the fulcrum, the balance point, the rock or the block you put under here. There's some movement here, maybe some slipping and rubbing and things going on here that aren't perfect. But essentially, the nature of the substance that forms the lever, because everything bends, even a steel rod bends a little bit, you're going to lose some of your force. When you calculate how much you actually get after those losses, that's what we call the actual mechanical advantage. In the case of the inclined plane, when you lift something straight up, you're lifting through the air, but when you slide it, here's my box, when you slide it up the ramp, there's friction rubbing on the ramp, which means you have to compensate for that friction force. So you're not going to get quite as much. Now here's the funny thing. Even with the friction, it can still be better than lifting. So we still do it because it's still better. The actual mechanical advantage is still better, a lower force than actually lifting, but it's not perfect. We lose something according to friction or due to friction. With the pulleys, these little wheels that are pulleys here, I'll put them in. Whoops, I just lost my page there. These little pulleys right here, these are wheels. And so they are rolling on little axles. And there's friction as they roll, they rub. There's little ball bearings usually inside that they roll around on. But still, a wheel, when it turns, it has to be connected to something and it rubs against the thing that it's turning around. So there's going to be problems there. When you think about a rope, this piece of rope, well, when I pull on the rope, perhaps the rope might stretch a little bit. Well, it might stretch before it actually grabs. And if the rope stretches, well, that's taking away distance because the rope might stretch before it begins to lift my load. And the stretching reduces the ideal mechanical advantage a little bit. The same is true with the wheels and axles and the gears. There are spinning wheels with axles. Those axles are going to have friction. So basically, ideal mechanical advantage is sort of like the theoretical best we could do. But the reality is we never get that because of the limitations of these things, the friction and the flexing of the wood, the tension, the stretching of the rope, and so on. And so what we normally have is a slightly less advantage, but it's still good enough. It's still better than having to lift or move these objects all on our own simply by lifting. So we're going to discuss each of these things, each of these machines, and look at how we might calculate IMA and AMA and how they might work. But the main thing for today is just to understand the idea of mechanical advantage, how it's a trade-off, trading more distance for less force. And these machines, or these little devices, are the things that allow us to do it. And they are the lever, the inclined plane, the string and pulley, and the wheel and axle. Those are the ones that we will look at.